Hello everyone, my name is Andreas Werdig and I'm presenting my final project, which is a Luigi workflow for image classification with TensorFlow. A typical image classification workflow is shown here, and it consists of many scripts that are available usually in different versions and need to be run for pre-processing the data and training a model. The versions of the scripts and the sequence in which they are called really matters, and sometimes pre-processing can be very time-consuming. Luigi can help here to determine which of the pre-processing steps are required for a particular model. The goal of this project was to create a Luigi workflow for image classification that starts from scratch, from an empty data folder and a predefined model architecture. All of the data are downloaded from a single website, and all of the necessary pre-processing steps and the training steps are implemented as Luigi tasks. The command line parameters allow training of different models or combinations of hyperparameters and models. Everything is implemented using the latest TensorFlow framework, and it is built in a Docker environment from the original TensorFlow Docker images. There's also an option to run TensorFlow GPU on a single machine or even a distributed GPU environment using the TF Estimator API. The output of the entire workflow is a single CSV file for each model that contains the validation loss and the accuracy for each model. I have divided the project into several task files, which I'm going to explain in the next few slides. The dataset is called the not-MNIST dataset, and it can be downloaded from the Kaggle website. It is very similar to the popular MNIST dataset. That one only contains numbers from 1 to 10, but here we have letters from letters A to J, as shown in the images, 10 classes, and so it's a little bit more complicated than just numbers. The training set consists of about 530,000 images. The test set has about 20,000 images. The first task downloads all of the data sets into compressed archives. And in the next task, all the images are extracted from the archives into folders that are labeled by the classes A to J. The output of this task is a CSV file that contains the path for all letter folders. In the next task, NumPy arrays are created for each letter, and they are then serialized after they're shuffled and then saved as pickle files. The output of this task is a CSV file that contains the path for all pickle files. Now, in the next task, the pickle files for each letters are opened and the images are shuffled again for each single letters and then added to, and all of the letters are added to a large NumPy array. After all of the letters are collected, the images are normalized in the range of 0 to 255 so that they can be saved as 8-bit images. And one-dimensional arrays with the labels 0 to 9 corresponding to the letters A to J are also generated. All of the data are then shuffled again to provide really good randomization, and then the data are split into a training, validation, and test set. The empty images, there are about 200 in this data set, are also removed, and all of the data are then serialized with the labels into a single pickle, salted pickle file. The next task converts the NumPy arrays into TF records data format, which is the preferred format to feed into a TensorFlow model. It is a very efficient data pipeline that prevents idle times and allows an efficient use of expensive resources such as GPUs or TPUs. The data are converted into 3 TF records files, one for training, one for testing, and one for validation. And the output of this task is a salted CSV file that contains the paths and the modes such as train, test, or validation. In the next step, that's the evaluation task. All of the training parameters, such as number of images per batch or the number of training iterations or log parameters, are defined. These parameters are currently hard-coded, but they could also be provided by an external file. In this task, The data input functions to read from TensorFlow TF records are also defined, and the model architectures are set up, as well as the optimization algorithms using the Keras API. This task does not generate an output because it is used as a parent class for the training task. In the training task, the model and its parameters are inherited, and the models are trained for a predetermined number of iterations. After training, a single output file for each model is generated that contains the history, um, and that is the evaluation accuracy and the evaluation loss for a predefined number of training steps. TensorFlow also generates a log folder with checkpoints and summary statistics that can be read in using TensorBoard, which is the TensorFlow visualization tool. The entire pipeline is kicked off from the command line using arguments that contain models or hyperparameters. And Luigi runs to all of the processing steps and then saves the output in a single folder. And that includes the evaluation accuracies and the TensorBoard summaries for each model. Taken together as a summary here, I have implemented a complete deep learning workflow that downloads all of the data from the web and extracts more than 500,000 images into labeled folders. All of the images are then collected from the folders and stored in NumPy arrays, and then they're preprocessed where all the empty images are removed and then normalized. All of the data is randomized and then converted into TF records, a serialized format that is then used to train two different model architectures and store the results for each model. There are a number of improvements I have thought about, but I was not able to do in the time that I had. One was the implementation of hyperparameter tuning by adding more hyperparameters to the outputs of the training task. And it would also be nice to store the training parameters, for example, the number of training steps or logging parameters in a configuration file. We could also add more salts to the outputs of the training task to capture changes in the version of the code, but also changes in the models or the data sets. I'm planning to publish this entire project on my GitHub page after the course. Thank you very much.